Okay, in this video we're going to look at some properties of the dot product, which will make using the dot product a little bit easier when we're working sort of with algebraic equations and things like that. So the first property we're going to look at is what we call the commutative property. Commutative property you can think of as basically meaning order doesn't matter. So what the commutative property says is that A dot B is equal to B dot A. And if you think about other operations like addition of numbers, right? If you add two numbers, order doesn't matter, right? 1 plus 2 is the same as 2 plus 1. Multiplying is a commutative operation, meaning order doesn't matter. Now some operations order does matter, right? Subtraction, order matters. If you A minus B and B minus A are not the same thing. So we're going to prove that the dot product is in fact a commutative operation. So the proof, let's say let A, now you could do this in R2 or R3. Just for the sake of simplicity, I'm going to do it in R2. You could do it in any dimension actually. But you'll see that it won't matter which dimension you do it in. It should generalize to higher dimensions. But A dot B, remember, is equal to, so it'll be A1, A2 dot B1, B2. So you multiply the x values, so A1, B1, plus A2, B2. But now each term here, so this is just regular multiplication, A1 times B1. Well, regular multiplication we know is a commutative operation. So you can flip the order here. But now that's just equal to B1, B2 dot A1, A2, because the B's are first. So that's just B dot A. So that shows you that, hopefully that shows you that dot product is indeed a commutative operation. Okay, now we'll look at the distributive property. So the distributive property says that A dot, and then if you take a bracket, B plus C is the same as A dot B plus A dot C. And the proof of this is very similar to the other one. I won't bother to redefine A and B, but C would be C1, C2. So you'll have A1, A2. Let me write it generally. So A dot B plus C, so this is the left side of this, would be equal to A1, A2 dot B plus C. So that would be the vectors B, C1, B plus C1, and then B2 plus C2. So now if I do the dot product, I'd be multiplying the x components, so that would be A1 times B1 plus C1 plus, and then you multiply the z components, A2 times B2 plus C2. So now you'd have to kind of do regular distribution, so the distribution of regular multiplication, which regular multiplication follows the distributive property. So that'd be A1 times B1 plus A1 times C1 plus, now distribute here. Alright, and now if I just sort of rearrange here, take A1, B1, leave that here, but now I'm going to write this one next. E2, B2, plus, and I'll write A1, C1, and A2, C2. Well, if I look at the first two terms and the second two terms, A1, B1 plus A2, B2, that's just the vector A dot the vector B, kind of by definition, right? Plus, and then here I have the vector A dot the vector C. Right? That's kind of the definition of it. So A dot B plus C is the same as A dot B plus A dot C. Okay, so that's the proof of the distributive property for vectors, for dot product of vector. Okay, another property for dot product is that the dot product is equal to the magnitude of a the dot product of a vector with itself is equal to the magnitude of that vector squared. And this one doesn't really, it's not really a proof per se, it's more like just a, if you do it, so A dot A, you'll see it's equal to this. So A1, A2, if I dot that with itself, then I would get multiply the x's, so that would be A1 squared, plus multiply the y's, so that would be A2 squared. And that's it. So that is the magnitude of A without the square root sign. So I've squared it, so I don't have a square root sign. So this property here, it's a useful thing to do. Sometimes in order to calculate the magnitude, you just think about it as the dot product squared, or sorry, it's the dot product of a vector with itself. But you'll see as we do examples how that becomes useful. There's another one. I don't want this video to go too long, so I'm just going to state this one. So the scalar multiplication over a dot product. So what it says here is if you do a scalar multiplication on a vector, let's say it was k times a, and then we dot that with another vector b, you can do the scalar, multiply the scalar sort of in any order here. So you could do a dot, and then you can multiply the scalar times b, and that would be the same. So if instead of doing the scalar times a, you did it times b, and then did the dot product, that would be fine. Or you could do a dot b first, so put that in the brackets, and then multiply that value by your scalar, and again you'll get the same thing. So I'll allow, that's actually going to be a question that I'll assign for you to prove it, but it's the same sort of proof as what you see up there. Okay. So when students first see these properties, a lot of times they'll think it's almost unnecessary to show them because it almost seems obvious that these properties will work, and because they work for regular multiplication on numbers, they work on dot product. So, and that's for the most part true. However, there's one property, and that's what we call associative, which does not hold for dot products, which does hold for numbers. What does the word associative mean? Associative has to do with if you multiply three things. So if you're multiplying three numbers, so let's say you're just multiplying a times b times c. So this is regular multiplication. A, b, and c are just numbers, real numbers. How do you do that? So the way you do it is you multiply the first two, get a result, and then multiply by the third. But associative means it doesn't actually matter which order you do it in. You could multiply the second two and then take that and multiply by the first. So that's what we mean by associative. Sort of order when you're multiplying three things doesn't matter. Dot product doesn't follow this rule, and I'll show you why. It doesn't follow it for a very particular reason. So a dot b dot c. What would happen if you tried to do that? Let's say you tried to do a dot b and did the first two, and then tried to dot product with the third one. This isn't even possible. A dot b, remember, is a scalar. It's a number, not a vector. So it doesn't even make sense to say the dot product of three things, because if you did the dot product of two, you'd get a scalar, not a vector, and you can't do the dot product of a scalar with a vector. Doesn't make any sense. So this is not even possible. So that's why it's not associative, because associative has to do when you're doing three things, but you can't do the dot product of three things, of three vectors.